In this video, we're going to discuss a common circuit behavior that will help us simplify the common emitter transfer function. We're going to talk about a circuit behavior called the Miller effect, and it's easiest to see the Miller effect in action using this super simplified single-ended ideal amplifier. We're curious how having this impedance Z in feedback around the amplifier affects the amplifier's input impedance. So we're looking at the impedance in here. Note that the input impedance would be infinite if we were just looking into this amplifier without Z. So Z is definitely going to lower our input impedance. The question is how much and why. We start that calculation by noting that our test current has to flow through Z. So we can find it just by taking the voltage. So we can do a current balance where IN is equal to the current through Z, and the current through Z is given by Vin on this side, minus A times Vin, which is set by the amplifier on this side, and we divide that by Z. That means we can do a simple rearrangement to find that Zin is equal to Z over 1 minus A. And this equation, or this behavior, is referred to as the Miller effect. This is super interesting. It means we can modify the size of the impedance perceived by Vin by changing A. That includes making the impedance infinite if our gain is exactly 1. That actually makes sense because if this node was exactly equal to Vin, then there'd never be any voltage difference across Z, so no current would flow through it. We can take this one step further and say that we can represent our circuit with a simplified version that pulls Z in out of feedback and instead puts it in shunt with the amplifier A here. This is called the Miller approximation. It loses some crucial information, like the fact that we'd expect Vin to shoot some current through Z into whatever was attached to this node. But getting rid of the feedback makes the circuit much simpler to analyze, so we're willing to lose that nuance in order to do make the math easier. I want to call out a few cool details about the Miller effect. First, note that if your gain is negative, which is the case for most of our amplifiers, then the denominator of the Miller effect expression adds together instead of subtracting. You wind up with a 1 plus A. And that's nice for analysis because it avoids the weird infinite impedance case that I mentioned earlier. Second, if your impedance Z is a capacitor, then your impedance is 1 over Cs, and you can flip the Miller expression upside down. And that means that your cap is equal to your feedback capacitance multiplied by 1 minus A, and that'd be the equivalent cap seen at the input. In other words, you perceive a capacitance that is bigger than your feedback cap by a factor of your voltage gain. This happens because the voltage gain increases the swing across the cap. So the total charge change it perceives is increased, right? If I go up by V in here, and I go down by AV in here, then I need to move a lot more charge through the cap to achieve that. And this effect is why C mu is so bad for amplifiers. It gets Millerized, which is this effect of making it bigger, which makes it seem much larger than C pi when the voltage gain is high. So, in summary, the Miller effect changes the input impedance of amplifiers with elements in feedback. That change in impedance comes from the gain of the amplifier increasing the swing across the element. And if you have the Miller effect applied to a capacitor in feedback and an amplifier with negative gain, it makes caps look bigger. And the schematics in this equation really summarize the Miller effect.